Hey geometry students, we are working on lesson 2.4, which is on page 49. We're going to start with page 49 in your student journals. I'm actually going to do something a little bit different. I'm going to ask that you pause the video and I want you to complete this page on page 49. I just want to see what you guys can come up with for responses, and then I'd like you guys to kind of check your answers here in a second and see what you guys get. All right, so pause the video, do what you can on this, what you get, and then we'll go through answers. All right, welcome back. I am going to go through answers. So basically what we're doing here is we're talking about kind of the beginning parts of writing proofs. So we're starting with something that we already know, like an algebraic equation. And they're asking you to kind of do the justification. Because when we do proof writing, what we're basically doing is we're justifying every one of our steps as to why we know it's true. And so a proof is just kind of like almost like a recipe, if you will, of exactly why we know we can do what we can, why we're doing the math. So for example, on this one, we wrote out the equation. So this is what we're given in the equation. And a lot of times, or in any proof, you're always provided with something that you're trying to, that you start with, that you're trying to eventually get to a goal. The next one, if you notice, what did we do to get from here to here? And so what I'm looking for is for you to recognize that you use the distributive property. So I know that you may not, it's been a while since you've talked about some of these properties from algebra, so that's why we're kind of reviewing some of this stuff. All right, so then from here to here, if you notice, the only thing we really did was we simplified the 6 minus 5. So I'm just going to write simplify. And if you wrote combine like terms, that's fine as well. Next, I'm going to, if you notice, what we did is we subtracted 2x from both sides. And so what we call that is the subtraction property, I'm going to abbreviate, of equality. So that's why we can do this. So like, how we do the inverse operation, right? What's the opposite of adding to x to both sides? It's subtracting. That's how we undo. So this is the property that allows that to happen. Okay, so then next what we did is, to get from here to here, all we did is we simplified, right? So we combined like terms. So we're going to use the word simplify. Next, I went ahead and subtracted 4 from both sides. So this would be the subtraction property of equality. Next, if you notice, all we did was simplify. We combined some like terms. And then to solve for x, you would tell me to divide both sides. So we call that the division property of equality. So same thing, like kind of like the inverse operation, right? So it's what we do when we are, we're trying to solve a value for x. And then we simplify it again. And then last, so notice that, so this is what the kind of the weird thing is about proofs. So we started with this was your given, right? And so a lot of times what we do in a proof, especially in a geometric proof, we give you kind of a starting point and we tell you what the end is. So this is what we call the given and this is what we call the proof. In other words, that's like your goal. So if your goal is to have it like this, x equals -1, and you have it as -1 equals x, technically you need to apply one more property. And we call that the symmetric property of equality. And so basically it's more like common sense, right? It's kind of like you could also maybe have called it the commutative property, right? So it's like the opposite function, but we call that symmetric. So basically all you're doing is kind of almost like you're reflecting those two values. And so it's important that your final answer is in the correct format. And I know that's really picky, but that's part of what we're doing with proofs. All right, we are going to skip ahead to page 51. So I'm going to skip ahead to page 51. And we're going to talk a little bit about some vocab, not much. So in this one, it asks for an equation. And this is what I want you to make sure you know about an equation. This is a difference between an equation and an expression. An equation has an equal sign. So an expression doesn't. So if I had so like the difference, if I had like 3x minus, 2 plus x, and I asked you to, simplify this, you would tell me this is 4x minus 2. You wouldn't be able to solve this, okay? The reason why you can't solve this is because there's no equation. There's no equal sign. If you had equals 10, now you can go ahead and solve that equation. And you could add 2 to both sides and divide by 4. So solving the equation is when you're finding the solutions that fulfill the, like basically you're solving for x. It doesn't have to be x, but you're solving for a variable. So you're finding the solutions, you're trying to find the values that satisfy the equation. And that's what it means to solve. So again, solving an equation, you have to have it be an equation. It has to have an equal sign. You can't solve an expression. You can simplify an expression. You can't solve an expression. A formula, you probably already know what a formula is. We don't really need to define it, but basically we have a million of those. It's just a relationship that it's expressed in symbols. So we'll just call it a math relationship or rule expressed in symbols. So for example, y equals mx plus b. We use this for linear, right? So we talk about m being our slope and b being our y-intercept. So this is a generic form for all forms of linear functions, right? So we didn't give a specific one. We didn't put like the number 2 here, number 5 here. That would be one specific example. This is what we call a generic form. All right. In order for us to do some of this stuff, we just need to make sure that we understand these properties that we just kind of talked about in the last page. So there's a whole bunch of them. So like the addition property of equality, the subtraction property of equality, multiplication, division, those are all kind of the same thing. Those are what we already been doing. We just maybe haven't like named the property, right? So if you add 2x to both sides of your equation, that's the addition property. If you subtract 5 from both sides of your equation, that's subtraction property. And so all of these properties, I think we already are pretty comfortable with. The substitution property basically says if A equals B, then A can be substituted in for B into your equation or your expression. So imagine like if you said, I don't know, I was giving you, 3x minus 2, and I said, let x equal -4. So we call this the substitution property. So what you would do is you would substitute -4 into your equation. So you would go, 3 times -4 minus 2 and go on. So that's what we call the substitution property. If we know that two things are equal, we can substitute it in. If I know x equals -4, then wherever x appears, I can put -4. Again, that's a common one that we've used a million times in our algebra skills, but like that's the actual property. I'm on page 52. So now we talk about the distributive property, which I'm sure most of you are familiar with, but basically we're talking about, getting rid of the parentheses here, A multiplying through, make sure that you multiply both values. You probably did this. It works for if you have a parenthesis that's positive or negative, no big deal. Something we're fairly comfortable with, I think. So then we have 3 other properties that are a little bit more, I would say these ones aren't as common. So reflexive property, symmetric property, and transitive property. So reflexive property. So a lot of people get reflexive and symmetric mixed up. So reflexive means something is equal to itself. So, A is equal to A. 2 line segments are equal, 2 lengths are equal to each other. 2 angles are equal to each other. So what you have to remember is like reflexive is like looking into the mirror, right? Like you're equal to yourself. So it always equals itself. Symmetric is when something equals, like it goes both ways. So if A equals B, then B equals A. So you're just kind of flip-flopping them. And again, you can work that with segment lengths, you can work that with angles. So they're not equal to each other, they're not equal to the same thing, they're equal to each other. So it doesn't matter which order in which you write it. The transitive property kind of goes back to that, laws of logic, right? So that laws of syllogism and law that we talked about in one of the last videos we did. So the transitive property talks about if A equals B and B equals C, then A has to equal C. So it's like if A equals 4, well, let me rephrase this. That's a hard one to kind of do. Maybe it's easier to look at segment length. So if segment AB is equal to segment CD, but CD is also equal to EF, then wouldn't it have to be true that those two things are equal to each other? So basically you're saying if two different values or two different segments are equal to the same segment, then they have to be equal to each other. And again, we kind of gave you an example with segments. We gave you an example with angles. It's a little harder to kind of think about with numbers, but same deal. So that's what the transitive property is. All right, let's go through an example or two. I'm not going to go through all of these again because I want to kind of have you guys do a lot of them, but let's go over number 1, and then maybe I'll go over number, let's do number 3 actually. All right, so let's do 2 of these. One's easier than 3, so let's start with number 1. So it says, solve the equation, justify each step. So 3x minus 7 equals 5x minus 19. So what might be helpful if you pull back that first page we did, remember when I asked you to pause the video? And so if you look back kind of like at this page where we kind of started, we're going to kind of do the same thing. So this one, we are just going to write, I'm going to write given, because we're given this equation. So that's our justification as to why we start here. It's because it was provided. Depending on what you think the next step would be, I would probably go 3x minus 3x. So what I would do is I would subtract 3x from both sides. I'm going to write it like they do, even though normally if I'm solving an equation, I don't write it like this. And then this would be that subtraction property of equality. And I'm going to do a lot of abbreviating here, so that means subtraction property of equality. And then I'm going to write negative 7 equals 2x minus 19. And the justification here was that I simplified. Okay. Next, I am going to add 19 to both sides. So this would be the addition property of equality. Again, I'm abbreviating. So then if I do that, I get what? 12 equals 2x. And so what I did here was I simplified. And then I'm going to divide both sides by 2. And again, I guess technically I should have written this. So that's the division property of equality. And then I'm going to write, 6 equals x. And I'm going to write that as we simplified. And then, I don't know, it didn't really tell us how they wanted the answer, but I guess in normal circumstances, we would write the x first. So I'll go ahead and do that. And so I will call this the symmetric property. So that's what you're doing for this. You're kind of just, so this is an algebraic proof. And so obviously the algebra here we know you can do, or obviously we hope you can do. It's not about you doing the, well, it kind of is, but it's more about you being able to justify your rationale, your response for those. And so we're looking for you to kind of demonstrate to us, like, how do you know you do what that you know to do that? Because when we get into writing proofs with geometric proofs, we are going to need to be able to justify our steps every step of the way. And some of it's going to be kind of like redundant, like you're going to be like, oh, well, that's silly. Why do we have to say that? But if you notice, every one of these justifications, there's a rhyme and a reason for it, right? We did simplify. That's how we got from this step to this step. And so a geometric proof is a very detailed plan, just like this algebraic proof was a very detailed plan. I want you to get in the habit of thinking this way so that when you do the geometric proofs, you don't skip any steps. Let's do one more example. Let's do the -5 2u plus 10 equals 2u minus 7. So this one is going to be, I'm going to go ahead and write this one out as this is our given. All right, so what I would do first is I would probably go ahead and I would get negative 10u minus 50 equals 2u minus 14. So what did I do there? I used the distributive property. Okay. Next, I'm going to probably add 10u to both sides. Let me use a different color just so you can see it. So I would do, I would do negative 10u, but then I would add 10u to both sides. So this is the addition property of equality. And then I'm going to simplify. So they're going to cancel, and I'm going to get negative 50 equals 12u, if I put those together, minus 14. And so what I did there was simplified. So next, I'm going to add 14 to both sides. So that would be my next step if I were to solve this algebraically, which I am. So then this would be called the addition property of equality again. And so I would get negative, what was that, 36 equals 12u. And that was simplifying. And then next up, I would take negative 36 equals 12u, and I would divide by 12. So this is the division property of equality. And so I would get negative 3 equals u, which is my simplifying. And then I would get u equals negative 3, which is that symmetric property. All right, so I think a practice would be great for this, not because I think you need to practice with the math so much, although that doesn't hurt, but it's more about you making sure you get all the steps. So there's a couple extra ones on this page. So basically this whole section is kind of the same deal. So you can do number 2, that would be a good one, and then you can try 4 and 5. All right, that's it for today. Thanks, guys.